Okay, so I guess we can start.
Yes, please go ahead. It's running.
Yes, okay, so Kyle, over to you. Toric ALCG2 manifold.
Yeah, perfect. Okay, so our story starts with this theorem that was proved early in the collaboration. So by Pascal, Haskins, and Nordstrom. So they looked at constructing G2 manifolds on circle bundles over Calabi-Yau threefolds, which are asymptotically conical. So such circle bundles are classified by their first Stern class. So in order to get a non-trivial bundle, you want a non-trivial first Stern class. And then they also need this topological condition that the first Stern class pairs trivially with the symplectic form downstairs. So once they have that, they create a one-parameter family of holonomy D2 structures on the circle bundle. And as the parameter goes to 0, this epsilon goes to 0, you get a collapsing in the Gromov-Hausdorff sense to the base. So the point of this talk is basically if we insist that the base is toric, then the circle bundle you get is also toric. So okay, first I have to explain what that means for a G2 manifold to be toric, and then I'll give a little sketch of the proof to explain some of the ingredients involved. And then most of the talk is actually going to be to try to draw pictures for the multi-moment map. You get nice diagrams to explain how these work. Okay, so first we have to define these things. So this comes from Madsen and Swan, and it's a natural generalization of the idea of moment map to higher degree forms. So here we have a closed K form tau, and torus action on the manifold. So this torus action can be used to generate these symmetry vector fields. And the idea is to plug in enough of these into your form until you get a one form. And then the condition that you want to have satisfied is that this one form is exact. And then this property is encoded in the multi-moment map, which is the potential for that one form, essentially. So you can think about it as a smooth map from the manifold to this lambda wedge power of the dual Lie algebra. And so this generalizes the usual moment map when k is equal to 2, and then the image is just simply the Lie algebra dual. Okay. And Madsen and Swan also apply this definition to the D2 setting. So they determine that the best notion of toric for a G2 manifold is when you have a three-dimensional torus acting, which is multi-Hamiltonian with respect to both of these closed forms that you have, the three form and its Hodge dual. And then you get these two multi-moment maps like this. And then we will find it more convenient to normalize these because the image spaces are kind of a little bit counterintuitive. But if we fix a volume form on our Lie algebra and just whack those in there, then this rho guy ends up having this real value, which is kind of more comfortable, and the new has the values in this Lie algebra, which is three-dimensional. So you end up with a three-dimensional part and then a one-dimensional part, and then together there's also the three-dimensional orbit. So add those all up to you get 7. So that's a good thing, because you actually get this a local homeomorphism of the quotient space into the image space when you just add together these multi-moment maps. So this is the same picture that you get from the symplectic picture, and it allows you to really think of the multi-moment map image as the space of orbits, just represented in a nice way. And we'll just denote this relationship with this kind of sequence diagram thing, almost like a fibration, but of course it's not every fiber is T3, and some collapsing at some point. Okay, so now we return to our our theorem that we want to sketch. So we have to understand a bit about how this construction works of the G2 structures before we can talk about what the toric business is. So we'll do that first. So the story really begins with an older theorem by Apostolov and Solon, which studied, again, circle bundles over a Kähler threefold. So then the G2 structure has to be given of this form, where you have on the base you have an ST3 structure and a scalar H, and then there's the connection 1 form for the bundles theta, and it's going to solve a bunch of equations. So these equations are what you need to make sure that it's how long the G2 is parallel. But we don't really care about the form of the equation, so we're just going to contract everything and just say some linear operator or differential operator vanishes. So in order to find this family of G2 structures, you do a series expansion with some epsilon parameter, and they do it in such a way that the symplectic form is fixed. So that we'll see that's kind of important. And then when you look at what this differential operator does to this system of tensors, you end up being able to inductively figure out how it works. Each of these terms is going to be a linear system of equations in all the lower order terms. And then there's a bunch of analysis that goes on to show that you get existence and uniqueness using the asymptotically conical condition. So that stuff works out very well. So now we ask what happens when it's toric. So first, what we mean by toric is it's just a property of the symplectic form. So there's this T3 which preserves symplectic form in the Hamiltonian way, getting a moment map. But there's also this complex volume form, and so you end up having a two-dimensional torus, which also preserves the complex volume form. And then if you take a quotient of these tori, you get a circle action, which just acts by changing the phase of the complex volume form. So it's all very well understood. And then the next thing to do is to try to lift somehow to make a torus action on the circle bundle M. So the way to do this is you take your vector field downstairs, one of the symmetry vector fields downstairs, and you lift it in such a way that preserves at least the first term of the connection, connection 1 form. So once you do this, you've already got the first term of the series expansion all already preserved by this lift that we've constructed, and then you can work inductively in the same way that these each of the higher order terms of the series expansion are created. Then if you try to push forward by our lifted killing vector field, you're just going to get a new solution. So by uniqueness, it must have been preserved. So you end up with the whole structure is preserved, and we've created our torus action by just taking these two-dimensional family of lifts as well as the vertical vector field for the circle bundle, which we will denote by V. Okay, so this is roughly how we show that the thing is toric, and now the next thing is to try to draw the pictures of the multi-moment diagram. So we're going to start very simply and give some basic examples of just symplectic moment maps, and then see how you can draw similar pictures when you have the Calabi-Yau structure. There's something slightly different that you can do, and then use that to build our intuition about what the G2 moment map work, especially in this example, in this set of examples. Okay, so we start with the very simplest possible example of a symplectic moment map. We have the usual T3 action on C3 with its usual metric, its usual symplectic form. So you get a very straightforward moment map, and which image is the octant. general, the moment map image would be locally like this, and it's going to be some kind of a polytope. It's usually denoted by delta, and so this affine space. So as I was mentioning before, the point of the moment map is this nice representation of the space of orbits, and then also the kind of combinatorics of the polytope tells you the stratification of the different orbit types. So it's usually encoded by making these normal vectors x for each of the codimension 1 faces. And then for each of the faces of the polytope, you can count like how many circles collapse at that point by how many of these these x vectors are normal to that face. So the generic orbit, nothing's normal, so you have a free action, and then on the other extreme, like at a vertex, then there's going to be n, or like 3 normal vectors, so it's a fixed point. And all the other faces have in-between behaviors. Okay. So yeah, everything locally looks like this, and then we might want to do desingularization. So you do that with blowups. So the way you would do that is you take any of your vertices, and then you can create a new face of your polytope by cutting with a hyperplane in such a way that the normal is the sum of the adjacent normals for your original vertex. So in this example, if you do such a cut of the octant, if you do a cut at height 1, then you end up with just the regular unit 5 here. And if you take the quotient by the corresponding group action corresponding to the normal, that gives you the hot vibration on the CP2. So you see this triangle that we've made by cutting is CP2. And then you can think of the blow-up as just being the space that I've drawn on this picture of the octant when you took this tetrahedron up, and you have to do this quotient here by the hot vibration on the cut-off end.
Okay.
Now what happens if you're in a Gonzalo setting where you have the SG3 structure? So you have some kind of a thing like this, and this is the symplectic moment map. But we also have this two-dimensional torus, which preserves the complex volume form. So we might want to draw a picture that is more focused on this two-dimensional thing. And so it turns out that you get a nice picture if you can make a mu bar to restrict the regular moment map just to the two-dimensional part, and then you get a multi-moment map zeta corresponding to the three-form omega, and this ends up being complex value because of this complex value volume form. And then so then you got a nice representation here of the T2 orbit space by these multi-moment map images, which we I denote by this dotted line kind of diagram. So how this works in practice is that the boundary of the symplectic moment map picture are going to be the parts where zeta is equal to 0. So if you take the zeta is equal to 0 slice, and then you have this kind of, now it's a two-dimensional moment map, then you get a kind of flattened picture of the boundary of the polytope. The picture that you get, and then this again kind of encodes the orbit stratification. And these have been studied in the physics literature, and they're called PQ webs there. So I think that's the reasonable thing to call them here as well. Okay, so the next thing to talk about would be what happens when it's the toric G2 manifold. So we'll start with the simple example where you take the natural G2 structure on the product of a Calabi-Yau manifold with a circle. So if the Calabi-Yau manifold is toric, then this thing would be natural to be toric as well. So we get this kind of commutative diagram, which describes the relationship between the Calabi-Yau manifold and then the G2 manifold, and then other parts too. So the thing that works well with the product is that the scalar terms are just very well related to each other. So here this complex value multi-moment map zeta. The real part would just be rho for the G2 moment map, and then the imaginary part is basically the quotient of the projection from the Lie algebra parts of the multi-moment map. So you end up with in this, for the product case, it's not that surprising, but you would get just a PQ web sitting in some plane inside this three-dimensional space at the part where rho is equal to 0. Okay, but then this diagram also will hold infinitesimally for any toric G2 manifold. So in general, you get some kind of three-regular graph that sits inside of the three-dimensional part of the moment map, multi-moment map. Okay. So, and then we can draw a similar diagram for our circle bundle, the construction that we do, the ALC guide. And we get most of the same picture, but we don't have the nice relationship between the scalar part. But we still do get a nice projection from the three-dimensional image onto the PQ web for the Calabi-Yau guy downstairs. And this is essentially because the symplectic form is the same. It doesn't depend on epsilon. So in order to understand what the pictures are for our G2 guys, we already know what downstairs looks like. So we just need to understand how these things look. So here's the example that the easiest example. So before this work that I'm presenting on, this was the only drawing of a toric G2 manifold that we knew. Okay, so I'll explain it. So you can take, to figure out how this relates to the picture downstairs, so we have this PQ web. You take any generator of one of the lines, and then you look upstairs, and then you can, you want to figure out what the slope is, and then you get this nice formula. So you have the connection one form that just evaluates at the lifted vector field, and then times by v, which is just the generator in this direction. So this is a nice formula, and the important thing that makes this formula extra nice is it actually doesn't depend on much. It only depends on the bundle, but it doesn't depend on this epsilon parameter for a family, and more importantly, it doesn't depend on theta. It just depends on the fact that d theta represents the first Chern class. So when we're actually looking at this construction, we don't have to compute what theta is. We just need to look at the topology and find some kind of a nice theta to sit in for it. So in this example, I've drawn the G2 manifold. Upstairs is the D7 family of G2 structures on S2 cos R4, and downstairs is going to be the PQ web for the small resolution of the conifold. The manifold there is this vector bundle over CP1. So topologically, the important parts are that it's just an S3 bundle over CP1, so we can just choose theta to be the Hopf vibration, and then once you get everything lined up, it's not too difficult to see how these slopes get put in. But more generally, we don't have to have just the Hopf vibration. We can have more complicated things. So, for example, you can make an asymptotically conical Calabi-Yau manifold by taking toric positive Kähler-Einstein surface sigma, and then taking the anti-canonical bundle of it. Canonical bundle. So this is just an example to say that we would care about bundles over surfaces. So in order to create the circle bundles, so we would do it like this. So you would the surface would be toric, so you're going to be able to draw some kind of a polytope for that surface. And then to create the circle bundle over it is basically the Booth-Rang construction, which creates a contact manifold over the surface. But this has been interpreted by Lerman in the toric setting. So in terms of in the toric picture, what you do is you have your original polytope, and then you take the cone over it, and that's going to correspond to some symplectic cone manifold, which is going to be 6-dimensional. And then what you do to make the circle bundle is then you just take the link of the cone and take the moment map image of that, the moment map for the cone. So this generalizes what we saw a few slides over, where we saw the hop bundle as taking a link of the octant as the cone for C3. So it's basically the same idea, but generalized. And then this also in Lerman's paper, we see you can figure out that you have a nice formula for this thing that we wanted to compute. This theta of the x, the lifted vector field, ends up being just evaluating the moment map at that point. So these are always going to be constant along the edges. So that's very good for us. So these are the ingredients that we need to do the computation. But we remember for the G2 manifold, we want to study it when this, not for the theta for some symplectic form, but the theta for the first Chern class for the bundle. And those are, because of the topological restriction that it needs to cup trivially with the symplectic form. It's not going to be positive. You can't represent it by a symplectic form. But everything here is linear, so you can just kind of do this computation for all possible symplectic forms, and then extend linearly, extrapolate in order to compute what we need, these lifting slope values for a G2 manifold. So we'll see that in an example, which I think is going to be my last slide. So if we take CP1 cross CP1 as our surface, then you want to construct a circle bundle over it. Then you look at the cohomology, it's just going to be Z2. And then we want our symplectic form is going to be of the form MN, which we can choose to be coprime. And then the first Chern class we needed to be orthogonal to omega, so that means it has to be basically in this form. So this gives these manifolds, which are called MMN by the paper by Foscolo, Haskins, and Nordstrom. These guys admit a co-homogeneity 1 G2 manifold. And then this is the picture that you get. So here we get the rectangle is the symplectic form in that basically for the surface, and we get these edges coming out of it, rays, and then it lifts, and you can choose your parameters in such a way that this is the picture you get. So basically, just you took the rectangle and it bends a little bit. Okay, I'll finish there.
Okay, thank you. Thanks very much for the talk. There was a question, I think we should have the answer. There was a question from Gonzalo, who asked a question about whether you can ever have a T4 action on the G2 space. I think the answer is no, right? In this situation, or possibly ever.
Yes, that's correct. I mean, oh, sorry, Gail, answer, sorry.
No, you can go ahead. You investigated that more than I did.
Okay, so what we show in our paper is that if you have a T4 action, it cannot act multi-Hamiltonian for both the 3 form and the 4 form. So if you want this parametrization, then the answer is no.
Okay, thanks. I think there's another question in the chat, but maybe it could be asked vocally. Are there any other questions in the chat that need, any other questions from anyone? I had a question. You started with the picture of the B7 family, the D7 family. What about the B7 family? Is that a similar situation, or?
Yeah.
You know, so one sort of goes off to, one collapses to, you know, S3 cross R3 maybe, and the other collapses to S2 cross R4 or something.
Yeah, so you could, but yeah, the B7 family, you could imagine taking the projection instead of down like this, but actually along this line segment that connects to these. So that ends up being the quotient that you get is the cotangent of S3. And then the PQ web for that ends up being actually 2 different levels, 2 different lines, which you can kind of imagine these flattening out. Yeah.
Okay, thanks. Well, if there are no other questions, thank you again for a clear talk. And